Look at a sweeping mountain range or a river carving its way through rock. We usually think about the physical world on a massive scale, shaped by slow, visible forces over thousands of years. But when you look closer, the rules get strange. You can pile sand up into a tall mountain, but a handful of water instantly collapses. And if you inflate a balloon, the completely invisible air inside it actually adds measurable weight. Take a glass of plain drinking water and drop in a spoonful of solid sugar. Stir it around for a moment, and the solid crystals completely disappear. They don't melt, they are just gone. Since solid matter can't simply blink out of existence, it must be operating on a hidden set of microscopic rules playing out right in front of us. Take a solid stick of chalk, snap it in half, and grind it with a mortar and pestle until you get a fine dust. Under a magnifying glass, you can see that nothing new has been created. The chalk hasn't changed its physical identity. Every tiny speck is still chalk, just reduced to its smallest possible physical unit. That is exactly what happens in the glass. The water didn't erase the sugar. It broke the large crystals apart into millions of constituent particles that are too small for our eyes to detect. At a microscopic scale, you can see where they hide. Water particles aren't packed perfectly tight. They have tiny empty pockets between them, known as interparticle spaces. When the sugar breaks apart, those tiny units slip right into the gaps. The smooth surface of a liquid, or even a hard solid object, is actually a matrix of separate, distinct pieces, separated by a surprising amount of empty space. This brings up an obvious problem. If everything is mostly empty space and loose dots, why doesn't an iron nail instantly collapse into a pile of dust when you hit it with a hammer? The answer is an invisible force pulling the particles toward each other, called interparticle attraction. In a solid state, this attraction is incredibly strong. The forces lock the particles into a rigid, fixed grid. They can vibrate in place, but they cannot move past each other. That tight grip gives solids a definite shape and volume. If you introduce enough energy to make those forces relax slightly, the structure breaks. The particles stay close, but they can now slide and tumble over one another. This allows a liquid to flow and take the exact shape of whatever container you pour it into. And if those bonds snap entirely, you get a gas. The particles shoot outward in all directions, bouncing off surfaces at high speeds. This is how the scent of a perfume travels across an entire room moments after you spray it. The air you breathe, the water you drink, and the phone in your hand are entirely defined by the microscopic tug-of-war happening between their individual parts. We use these microscopic forces to our advantage all the time. Think about trying to wash a heavy grease stain out of a shirt. Water alone won't work because it repels oil, but soap particles have a unique structure. One end is attracted to oil, and the other is attracted to water. The soap particles surround the grease, attach, and use the rushing water to drag the oil off, literally tearing it away. This helps us solve everyday visual riddles. Pour a bag of dry rice into a jar, and the grains flow and fill the shape of the container perfectly, acting exactly like water. So, is rice a liquid? Not quite. While the macroscopic pile shifts and settles, the individual grains making up the pile do not change. The interparticle attraction inside a single piece of rice is tight and unyielding. The pile moves, but the individual units making up the pile are solid. The stable, predictable world we navigate every day is a macro illusion. Everything around us is actually a buzzing universe of particles, constantly vibrating, sliding, and colliding, hidden just out of sight.